PDF. So what I've done is I've just kind of screenshotted several of the problems, and I don't have all the problems screenshotted. So if there's a multiple choice question on here that you don't see that you wanted me to go over, I'm very happy to go over it. I just will kind of have to wing it as far as like, we won't be able to look at the exact, I guess I could share my screen. It'll just be a little more tricky, but I can totally do any of the problems. So, all right, well, I'm gonna go ahead and share my screen with y'all. Chat, I'm in an in-person class, so I cannot say, could you happen to record it and post it? Oh, sorry, that was a private. Yes, this will be. Okay. Oh, I guess they already left. Okay. Somebody's asking if we were going to record it and post it. And yes, this will be recorded and posted as well if you have to go at any point. So let me share here. All right. Most of the multiple choice questions, well, the ones I think I have here for us to go over, it says which question it was, but it was more so the ones that involved a little more math. I think I actually only have 2 of the multiple choice questions. So I'm just going to work through these. I have all the file response questions on here, and I'll work through those. And I'm going to pull the chat up as well, so I like to be able to see that while I do these. If you need to stop me at any point on the chat, or there's not a ton of us here, feel free to just unmute yourself and ask me questions verbally if you need to. So here we go. Question 11 on the exam. So this multiple choice was a density problem. So there's quite a bit of density stuff on the exam, and that was on purpose. Density is a concept that plays into the healthcare profession in many ways, whether you're a nurse or not. Okay, we have actually quite a few communications. I didn't realize how many as I've been looking at the discussion boards. There's a ton of you that are headed to communication sciences, but density is a very important concept, so that's why I had a lot of it on the exam. This problem said the density of a liquid morphine solution is 100 gram per 5 milliliter. So there's our concentration. It's a relationship, 100 milligrams of drug, morphine, in 5 milliliters of solution. It says an effective dose of morphine for a male athlete with an ACL tear is 0.25 grams, okay? Now, in real life, you would also have to take into account the weight of the person. And I didn't put something like that in this problem. But it says how many, so here's our question, how many mLs of morphine solution should the athlete receive? So I don't know if you remember when we talked about density, we said there's gonna be times we use density as a conversion factor, and that's what we're gonna do here. We're gonna use the density, which relates the milligrams and the milliliters, to convert from a mass to a volume. All right, so we're given 0.25 grams. That's how much the athlete needs to receive. So we need to convert this to volume in milliliters. All right, now density relates milligrams to milliliters. Well, we're given a mass in grams. So the first step is that we need to convert, from grams to milligrams. So we need the relationship for that. And it is 1 gram equals 10 to the power of 3 or 1,000 milligrams. So the first thing you should have done is grams convert to milligrams. 1 gram being 1,000 milligrams, okay? So grams will cancel, but I'm not gonna stop here. The next thing that I'm gonna do is I'm gonna convert using density now to milliliters. And I'm gonna use this relationship right here. So 2, we had 100 milligrams for every 5 milliliters. So I'm gonna put 100 milligrams on the bottom, 5 ml on the top. Now milligrams cancel, and we will get an answer with units of milliliters. So when you do the math here, 0.25 times 1,000 divided by 100 times 5, you should have gotten 12.5 milliliters. Okay, so that was A. Any questions there? All right, well, if not, we will move on. Next question. This one was one of the commonly missed multiple choice questions. I haven't looked at the exact stats on this yet because I'm not done grading, but I'm interested to see what they are. So this was just an electron dot structure question. It says lithium and oxygen form the ionic compound Li2O, a component found in minerals. Which of the following correctly displays the electron dot structures of the two ions that make up lithium or Li2O? So we know lithium, I'm just going to draw the electron dot structures before they become ions. So we know lithium is a main group 1, so it's got 1 valence electron, and oxygen is a main group 6, so I'm going to give it 6 dots. All right, so that's how they start out, and these are just the neutral atoms. Now, when they form the compound, we know that an electron is given away and received by these atoms. Okay, so lithium is going to become the cation. It's a metal, so it will give away an electron, and oxygen is going to become the anion. So it's going to receive the electron. Now, lithium, what we're going to have is we're actually going to have 2 of these, and they're both going to give 1 away because we see that the final compound, the formula is Li2O. We have 2 lithium cations, 1 oxygen anion. So we're going to have both of these lithium cations giving away 1. Their only valence oxygen is going to accept both because it has 6 and it wants 2 more. So when that's done, you will have 2 lithium that they're a plus now, and they have no valence. Essentially, they've given the 1 they had away. And then you have oxygen is going to have accepted both of those, so it will have 8. Now, if it's accepted 2 negative charges, it's a -2 overall. All right, so the one that matches that, if you look at number 1, this one is not the ions. This is the electron dot structure for the atoms, not the ions. So it's not number 1. Number 2 here, lithium is correct, but oxygen is not. If it's a -2 charge, it should have a full octet. All right, so we only see 6 dots around oxygen on number 2, so that part's incorrect. Again, lithium's correct on 3, and if you look at oxygen, that matches what we drew. So they're both correct here, and the answer choice should have been, oh, sorry, no. Should have been C, number 3. Okay. All right, 4 doesn't even make sense with what we're doing. It was kind of just a random. I hope nobody picked 4. All right. Any questions on that one? Okay. All right. This one was the naming. So write the corresponding name or formula. I was super bummed that Blackboard does not allow you to put in subscripts in your answers. So I hate that y'all had to type them in actually. One that was missed here is the very first one, okay? Ammonium oxide. So that was the most commonly missed problem here. So what is ammonium? It was a polyatomic. Now you have your notes. I encourage you to memorize these so that you know them and you can quickly move through these. If not, you had to spend quite a bit of time looking them up and writing them down correctly, but ammonium, so number 1, we'll just write it down here. It's NH4, and it has what kind of a charge? It has a +1 charge. All right, oxygen as an anion, oxide, is O with a -2. So many people wrote this, NH4OH. Why is that incorrect? We're not talking about hydroxide, we're talking about just oxide, ammonium oxide, not ammonium hydroxide. So a lot of people wrote that. That was wrong. When you put a +1 and a +1 cation and a -2 anion together, let's get this over here. what do you get? You need to have 2 of the cations and you need to have 1 of the anions coming together to form the compound. Now, because we needed 2, and remember, you can do the switch trick. You look at the charges on the opposite ion and it tells you how many of each you need. Okay, so because we need 2 of our cation and this cation is a polyatomic, we have to use parentheses. So you should have put NH4 in parentheses and put the 2 outside of that. And then you write the anion. Okay, so that was number 1. Number 2, we had barium iodide. Okay, so barium, if you look at the periodic table, is in main group 2, and it's Ba. If it's in main group 2, how many valence does it have? It has 2 valence electrons. So what do we know about main group 2? They're going to give away both of their valence, and what that means is they will form a cation with a +2 charge. Now we also have iodide, which is group 7. It has 7 valence. To become like a noble gas and stable, it needs 1 more electron. When it gets that, it will be a -1 anion. Okay? If it had 7 valence and you give it 1 more to complete the octet, it's a -1. So now you do the switch trick, or you figure out how many of each do I need to form a neutral compound overall. We're going to need 2 of our anions here to balance the +2 cation. Okay, 2 times -1 is -2, and +2 and -2, that adds up to 0. Okay, so we will be looking something like this, Bai2. All right, so that was number 2. Number 3, and I'm going to zoom in so I write smaller because I'm running out of space. COOH with a 2 here. What is CO? Most everybody got it right, but I had a few people guess copper. CO is cobalt. So all you had to do is look at the periodic table, that resource page that I provided for you, and you should have seen that it's cobalt. So you write cobalt. When we write the name of an ionic compound, you write the cation first. But what you should have also noticed about cobalt is it is a transition metal. Okay, it's in that transition metal block in the periodic table. So that means it could form more than one kind of cation, a +1, a +2, a +3, multiple charges there. So we need to indicate with Roman numerals what the charge on cobalt is. How do we figure that out? How do we know what charge it has? Well, here you should have known, you should have recognized the anion because it was a polyatomic and it's one I asked you to memorize. So looking at OH, all right, we know OH has a -1 charge. And how many of them are in this formula? There's 2, all right? So that means if we have 2 of these, 2 times -1, the magnitude of negative charge in this compound is -2. How many cobalt cations do we have? If you look at this, I kind of wrote all over it, but if you look at that, there's just one cobalt cation. So whatever the charge on that cobalt is, because there's only one, has to balance the total magnitude of negative charge from our anions. So essentially what we're saying is -2 plus what gives us 0? Well, it's obviously a +2, okay? So it should be cobalt-2 hydroxide. All right, questions there on how we figured out the charge on cobalt? You had to indicate, if you did not indicate that with Roman numerals, then you didn't get full credit for that. All right, number 4. We have our cation, Ca is calcium, so it should have been calcium. Calcium is a main group cation, so we do not need Roman numerals here. Then you should have recognized HCO3. I told you that I commonly use bicarbonate, but if you wrote hydrogen carbonate, I gave you credit for it. So it should have been calcium bicarbonate. All right. Now the fact that there's 2 bicarbonates here, that doesn't matter because these ions have set names. Calcium, we don't use Roman numerals. We never have to. It's a main group, so it's just calcium. And then the HCO3 has a set name. It's either hydrogen carbonate or bicarbonate. So you could have written calcium, hydrogen, carbonate. Okay, either one was accepted. All right, lastly, see if I can squeeze it in down here. We have Cr2SO43. I think this one was probably the most complicated. Challenge problem. So, Cr. If you look at the periodic table, Cr is chromium. All right, then you had to ask yourself, is this main group or transition metal? And you would have noticed it's I hear my newborn. It's a transition metal. Okay, so we're going to have to use Roman numerals to indicate the charge. So how do we do that? Well, let's look at the anion. It's sulfate, SO4. Okay, I'm going to over here, SO4 has a -2 charge. All right, now how many sulfates, if we go back and look, how many sulfates do we have in this formula? We have 3, okay? This 3 right here indicates that we have 3 sulfates. So if each one is a -2, 3 times -2, that's a total magnitude of -6 charge. All right. Now remember, we're charge neutral here. So however much positive charge we have balances that. So when we look at the cation portion, in fact, I'm gonna move some of this up. When we look at the cation portion, Cr, we know that it has to add up to +6, okay? Because that equals 0. Now the question is, how many do we have, and what is the charge? All right, so this is the number of cations in the first blank, and this is the charge in the second blank. So if we look at the formula, we see that we have 2 of them, right? So that's the number that we have, and 2 times what is +6? Well, we know 2 times a +3 is a +6. So each one had a +3 charge. And you had to indicate that when you wrote the name. So it's chromium 3 in Roman numerals sulfate. Okay. So here were the answers. And then these 3 down here. Any questions on the naming part? These rules and this stuff will not go away. We will be doing this all semester long. So if there's any misunderstandings, misconceptions with these, make sure you sort and smooth those out before we get to exam 2. Okay. This one, I don't know if I really need to go into it. If anybody wants me to, I will. I'll kind of talk about it for a second. Basically, we had these 3 isotopes, and I just wanted to make sure that you understand how we read and communicate isotopes and what that means. So I wanted you to tell me how many protons, neutrons, electrons are in each isotope, and then for one of them, actually for all 3 of them, tell me the mass number. If you guys remember, mass number equals the number of protons plus the number of neutrons. All right, that is the mass number. It's all simple math, no algebra here, just we had to understand its atomic structure. And then the number of valence electrons, so that is going to be different from the number of electrons. The number of electrons, okay, should be the same as the number of protons, right? But the number of valence electrons depends on what group it's in the periodic table, what main group it's in. So I'll do the first one, and then hopefully if anybody wants me to do the next ones, I can. But so for C13, if you look at the periodic table, I actually don't have one in front of me. I believe there's 6 protons. Okay, so the number of protons should have been 6. The number of neutrons, how do we figure that out? Well, this number up here, when we communicated the name of the ion or the isotope, C13, that is mass, right? So I gave you one of the answers just in the way I stated the isotope. C13, we identify isotopes by their mass numbers. So that means 13 equals the number of protons plus the number of neutrons. So if we know that there's 6 protons, to get the number of neutrons, all we do is 13 minus 6, which equals 7. There were 7 neutrons in there. We see the number of electrons is already given to us. So the mass number in all these cases was also given to us. It's just 13. And the number of valence electrons, well, carbon is in main group 4. So it has 4 valence electrons. So that was how you were supposed to handle all the blanks for this problem. Neon, and then we had a sulfur isotope. Any questions on those? I think he's asleep. My newborn, that is. All right, well, we'll continue. Certain insulin medications for diabetic patients have to be stored at temperatures below 40 degrees Fahrenheit. You are at a type 1 diabetes research clinic where the cooler reads 285 Kelvin. Can you store any insulin medication in the cooler? This is just a temperature conversion problem, okay? So what did we need to do here? In fact, I'm gonna pull something up really quick for this. Just one moment. Actually, I'm gonna grab our equations. I don't know if I can copy them. Here is the key, by the way, that I wrote out. So I wanted to, well, I'll just sub it in. When we're converting, so we're given a Fahrenheit, let me go back to my note. So when we're converting from Fahrenheit to Celsius, we have our Fahrenheit temperature here. Oop, we have to figure out what equation we need. I gave you those 2 equations, all right? And it looked like this. The one that we needed looked like this. Okay, so if we want a temperature in degrees Celsius, we're given a temperature in Fahrenheit, then you plug in your, sorry, I think I have that flipped. There we go. Because Celsius will cancel now. People did this different ways, honestly. Some people took 40 degrees Fahrenheit and converted it to degrees Celsius. And then from there, they converted it to Kelvin. The way I solved it is I took the Kelvin temperature. So I'm going to move all this down real quick. I took the Kelvin temperature and I converted to Celsius, and then from there converted to Fahrenheit, and then I compared it to 40. So you could have gone either way. So the way I solved it is I took 285 Kelvin, whoop, and how do we get Celsius from that? You subtract off 273.15, and that is going to give you a temperature in degrees Celsius. So do that, 285 minus 273.15. You should have gotten 11.85 degrees Celsius. So that is the equivalent temperature in Celsius. Now we need to take that Celsius, we're going to plug it in right here in the temperature equation, conversion problem from Celsius, and we'll get a Fahrenheit temperature. So you do 9 degrees Fahrenheit over 5 degrees Celsius times 11.85. Don't forget your units. Then you'll add 32 in the end. So 11.85, notice what happens to the unit of Celsius. You have it on top, you have it on bottom, those cancel out. So 11.85 times 9 divided by 5, and then add 32, and you should have gotten 53.33 degrees Fahrenheit. So this is the temperature of the cooler with Fahrenheit units. Okay, so this one is the cooler. Now, the medication needs to be stored at 40 degrees Fahrenheit or below, actually below 40. So because the cooler is higher than 40, you cannot store the medication in the cooler.
I have a question.
Yes.
So I might have just really done this completely wrong. I came out with the same answer, but I started by converting the 40 degrees Fahrenheit into Celsius,
Mm-hmm.
converting that to Kelvin,
Yeah.
and then comparing those. Is that okay as well?
Yeah, you can do that. In fact, if you worked it that way, that's totally fine. So what you did is you took 40 degrees Fahrenheit and you subtracted 32, right? And then you multiplied it by 5 degrees Celsius over 9 degrees Fahrenheit because you want Fahrenheit units to cancel.
Yes, ma'am.
So you got 8 times 5 is 40, 40 divided by 9. You should, so this is 40 minus 32 is 8 times 5 over 9. And you should have gotten 4.44 is a repeating 4 degrees Celsius. Okay, now how do you get a Kelvin temperature from Celsius? You do 4.44 plus 273.15, and you should have gotten, 277, 278, 270.
277 point.
Yeah. 277 point what?
594.
59. We'll just go with that. And that's Kelvin right there. So then 277.59 Kelvin. This is less than 285 Kelvin. All right. So the cooler is hotter than that. The cooler has a higher temperature. The cooler needed to be below 277.59 for you to store the medication there, but because it's higher, you cannot. So that's perfectly valid too. Does that help, Hannah? Uh-huh.
It does. I was just making sure that you'd accept both ways, I guess.
Yes, I accepted both.
Thank you.
Yep. Okay, next problem. You should have recognized this one. All right. This was a mimic of a homework problem from Mastering Chemistry. And in fact, it was the homework problem I got the most questions on. So I thought, well, one, it's good students are asking questions. But two, I like to do that. Sometimes I'll pull problems directly from the textbook. Sometimes I'll pull problems from Mastering Chemistry. So I do that because if you know how to work those things, you should do well on the exam. Let's look at this. Blood serum in healthy adults contains approximately 4.1 milligram per milliliter of sodium ions and approximately 2.9 milligram per milliliter of chlorine ions. So I changed the numbers here, but it's the same exact type of problem. You'll work it the same way you should have for the homework. What volume of blood serum would be needed to obtain 60 grams of sodium ions? What volume of blood serum would be needed to obtain 90 grams of chloride? And report your answer in liters, okay? So what we're given in the first statement, the two things I underlined, those are the relationships we are going to use. It tells you how many milligrams per 1 ml of blood serum. So if we're doing the first problem, we'll do the sodium portion first. You could start different ways, but if you start with the grams, 60 grams of sodium ions. To use our conversion factor, we're given a different unit of mass here. Grams and milligrams are both units of mass, but to use this relationship, we have to be in units of milligrams. So because we're not in milligrams, the first step is to convert from grams to milligrams, and I want to cancel grams, okay? So if you know that relationship, for every 1 gram, you have 1,000 or 10 to the power of 3 milligrams. So when you do that, grams cancel out. Now I can use this conversion factor and I can convert to milliliters because this relationship tells me how many milligrams per milliliter. So I can cancel milligrams and I can convert to milliliters because I want to report my answer as a volume. So this is letting us convert to volume. We'll have one more step, but we're almost there. So 4.1 milligrams of sodium ion for every 1 milliliter of blood serum. All right. So now we have canceled out milligrams, but it says report your answer in liters. So the last and final step was once you were in terms of milliliters to convert from milliliters to liters. So you needed to know the relationship there, and that is this: for every 1 milliliters, or 10 to the power of 3. Okay. Or, different people know it different ways. 1 milliliter equals 0.001 liter. That's fine too. I saw that. Milliliters cancel out, and then you'll be in liters. So you do 60 times 1,000 divided by 4.1 divided by 1,000. Essentially, the thousands cancel out. So you just do 60 divided by 4.1. And you get 14.63 liters. Here's the danger. Here's what I commonly saw. People would work this problem. They would start with 60.0 grams of sodium, but then they would say grams to, they would write like grams to milligrams. They would do that, but then they would put like 4.1 milligram per milliliter, and they would put it all in the bottom like this. Or even if they didn't put it in the bottom, when they wrote in this relationship, they would write the units together like that. You can't do that. That's going to mess you up every time. Whenever you see a relationship like this, and I give it to you in the problem, milligram slash per ml, you need to separate, okay? Separate the units. One goes on top, one goes on bottom. Do not write them like that. It'll throw you off, okay? And people who did, it did throw them off. So, all right, you're gonna work the second part of this problem the same way for chloride or anions. So we're looking for 90 grams here. That's a lot of chloride. So, oh, forgot the units. 90 grams of chloride ions. So the first thing, if we're going to use this relationship, 2.9 milligram per milliliter, we need to first be in units of milligrams. So the first step was to convert from grams to milligrams. So for every 1 gram, there is 1,000 milligrams. Grams cancel out. Now we can use the relationship for the chloride ion. So for every 2.9 milligrams of chloride ion, that was found in 1 milliliter of blood serum. Milligrams cancel. We're in milliliters. The last step to get our answer in liters was to convert from milliliters to liters. So 1,000 milliliters in 1 liter. And milliliters cancel out. Okay. And here, 90 divided by 2.9. I think your answer was like 31 point something. Essentially, you're doing 90 divided by 3, right? Almost. Do y'all ever go to, I have my alarm app and my calculator app right by each other, and they're both black and white. So many times I'll hit my alarm app and I'm trying to get my calculator. So 31.03, I don't remember how many decimals I put, but that's liters of blood serum. Okay, so that was how you work these problems. Questions on this? So again, the most common thing that I saw was people writing in those relationships and putting the units either both on bottom or both on top. And then you were still trying to cancel things. You would have already canceled, one of the two, milligrams or milliliters, but you couldn't because they were both stuck together. And so then it led to people throwing in additional numbers as they were trying to cancel units that would have already canceled otherwise. So questions there? Okay. Let's look at the next one. It says the specific heat, so this was a specific heat problem. You needed the equation of butter is 0.65 calories per gram degrees Celsius. Here's our question. How much energy in calories? So we are going to get an answer with units of calories. How much energy is needed to heat 12 tablespoons of butter for a batch of chocolate chip cookies you're preparing for your friend or your chemistry instructor from 21 degrees Celsius to the melting point of butter, which is 95 degrees Fahrenheit. So I complicated this problem a couple of ways. I added in some steps, but all of it are steps that you know how to do and had honestly performed earlier in the exam. You had to convert from volume of butter to tablespoons to grams to mass, all right? And you also had to convert from Fahrenheit to Celsius, okay, before you could plug things in. So there were some additional steps before you could do this problem. So first, let's write out our specific heat equation. Specific heat equals, here we're going to be in terms of calories. Calories per gram times change in temperature, degrees Celsius. We'll come back to that. We're actually really quick before we move on. We're solving for calories, so let's go ahead and rearrange our equation to get calories by itself. So to do that, you should have multiplied both sides by gram times degrees Celsius. Those cancel over here. And then what that leaves you with is grams times change in temperature times the specific heat equals calories. So now we need to ask ourselves, do we have all these things? Do we have the grams? Do we have the change in temperature? Do we have specific heat? Well, we're given specific heat flat out. So we'll just plug that in when the time comes. But we don't have the change in temperature in degrees Celsius. So we needed to take 95 degree Fahrenheit. All right. The first thing we needed to do is subtract off 32. And then we needed to multiply by 5 degrees Celsius over 9 degrees Fahrenheit. That's the equation. Because we got to get this in Celsius. To find the change in temperature, both temperature terms have to be in Celsius. All right. So 95 minus 30, 65 minus 2 more, so you should have got 63. And we still have degree Fahrenheit here. And then you're multiplying by 5 over 9. And the degrees Fahrenheit, you notice, will cancel out, leaving you with degrees Celsius. And I believe you should have gotten 35. Okay. Now, what is the change in temperature? The change in temperature is the final temperature, or sometimes you'll see it written as T with a little f here, T final, minus the initial temp, okay, or T initial. So the final temp was 35 degrees Celsius minus the initial, which was 21. The problem gave that to you, degrees Celsius. So your change in temperature should have been 14 degrees Celsius, all right? So here we will plug in our change in temperature, 14 degrees Celsius. Here we'll plug in our specific heat, 0.65. And now we need the grams, okay? Well, if we go back and read the problem, here's how much butter we have. We have 12 tablespoons of butter. That's some good chocolate chip cookies, right? But we don't know how many grams that is. However, the additional information tells us that 1 tablespoon is 14.2 grams. So we need to convert. So to get the grams, what we do is 12, I'm going to abbreviate TBSP, tablespoons. Our conversion relationship is for every 1, 14.2 grams. Tablespoons cancel. I think it was 170.4, is that right? Let's look at my note. Yeah, 170.4. So now we have grams. Now we just plug it in and we're good to go. You plug it in right there. So we would do 170.4 grams times 14 degrees Celsius times the specific heat, 0.65 calories per gram degrees Celsius. That's going to give us calories. All right, now let's make sure all of our units cancel. Grams on top, grams on bottom, degrees Celsius on top and bottom. So 170.4 times 14 times 0.65, and it was 1550. What were the unit or the decimals there? 0.64. This is how much energy, remember calories is a unit of energy. This is how much energy you need to invest in that butter to heat it up from 21 degrees Celsius to melt it, okay? Although I will tell you, in my time of making chocolate chip cookies, the best, fluffiest chocolate chip cookies are when you don't completely melt the butter, you just soften it. Actually, if you just set it out and let it get to room temperature and then make your chocolate chip cookies with non-melted butter, I'm telling you, take my word for this, you will like your cookies better. Don't use melted butter, just softened butter. Okay, and in lieu of all the chocolate chip cookies we're making and eating, now we have a problem about diabetes. In a diabetic adult, any questions on that previous problem? That was quite a bit of work, okay? So that one was worth, I think, 10 points. Well earned 10 points. All right, here's another conversion problem. In a diabetic adult, the level of blood glucose, blood sugar, can reach 200 milligrams of glucose per deciliter of blood. If an average body contains 11 pints of blood, how many grams and how many pounds of glucose are present in the blood? You should have also recognized this problem if you did the practice problems from the textbook that I suggested. Chapter 1, number 104, at the back of chapter 1, is almost this exact same problem, just different numbers. So I'm telling you, if you will do those practice problems, it's worth it. You will have an easier time on the exam because you might see some things. I'll always change the numbers. I'll never do things exactly word for word, but it will pay off. I really like this problem, so I just reconfigured it a little bit, but it was the same approach. So we have a relationship here, 200 milligrams of glucose per deciliter of blood, and then we're given quite a bit of additional information, and we will use these. So here's all of our additional information. First, we're going to solve for how many grams. Notice there's 2 questions here, so you should have reported 2 answers. How many grams? All right, so I'm going to have to convert. If I look at my very first relationship given, the amount of glucose is given as a mass, okay, but it's in milligrams, and I want my answer in terms of grams. So what does that signify? Is that we are going to need a relationship, I'll put it down here under additional information, from grams to milligrams, and we know that 1 gram is 1,000 milligrams. All right. What else? Are we going to need anything else? I think that's it. I think we can do the problem with all of this now. So I'm going to start with the first conversion problem given. If you remember the tips for conversion problems, I said usually the good place to start is the first conversion problem given, but I need to make sure that grams is going to be on top. Okay, so if I write it like this, 200 milligrams per deciliter of blood, I know that when I convert from milligrams to grams, I will put milligrams on bottom, grams on top, and I will end up with grams on top where I want them. You don't have to start here. You could have started other places, but this was an okay spot to start. So 1,000 milligrams for every 1 gram. Now I'm going to cancel everything else but grams, all right? So right now, milligrams cancel. I have grams on top. That's good. That's where I want it. I don't want deciliters in my answer. So I need to convert from deciliters. The only relationship I have is 2 liters. That's going to let me cancel out deciliters. So for every 10 deciliters, and plus the question's asking how many grams of glucose in that average body. We don't want to know how many grams per deciliter. We want to know how many grams of glucose per body. So we need to account for the full volume of blood in that body. And it's not just 1 deciliter. So 10 deciliters for 1 liter. Now deciliters cancel. Well, if we stop now, we have how many grams of glucose in a liter of blood, but the body contains more than 1 liter. Okay, we don't know how many liters, but we know it's 11 pints, and 11 pints is more than a liter because there's 2 pints in 1 liter. So we need to cancel out liters. We don't want units of liters in our answer. So I'm going to use the next relationship given. 1 liter is 2.11 pints. So liters cancel. Now the last thing is actually tucked away in the problem here. 11 pints of blood in an average body. So 1 body, you could have written this out, you didn't have to, equals 11 pints. As long as you canceled pints in the end. So you could have just written 11 pints. Okay, if you wrote it per body, that's fine too, but you could have just multiplied by pints here to cancel pints. And now we're gonna grams per 1 body. We're gonna have units of grams in our answer on top. So you do 200 divided by 1,000 times 10 divided by 2.11 times 11, and you should have gotten 10.43. Okay? So that was the first part of the problem. Now we have one more step because it says also how many pounds of glucose is this? So I'm going to use the last conversion problem, 10.43 grams. Now here's what I saw a few people do. They said, this is how many is in 11 pints. You don't need to do that. We're not concerned with how many pints are in. In fact, if you divide by 11 here, that's gonna throw off your answer. We just need to take that value of grams. Okay, and convert to pounds. So for every 450, the relationship is right there given to you. For every 453.592 grams, that's 1 pound. And I think the answer was like, it's a very small number, 0.023. Okay, so you had 2 answers here. There was grams, there's pounds. Any questions on that one? Well, that brings us to the last problem. You had, and again, I told you there's a lot of density material on this exam, and the last problem was a density problem. I wanted you to order these substances from most dense to least dense. I gave you a tip there. All you had to do was calculate the density and compare substances A, B, C, and D. So for substance A, you were given three lengths. So we had to calculate the volume in cubic centimeters. So 2 times, well, let me write my units. 2 centimeters times 3 centimeters times 1 is 6 cubic centimeters. And 4 grams. We know density, remember, density is mass. So that's the grams part divided by volume. And that is the cubic centimeters part here, or milliliters. Remember, you needed to remember for this one, 1 cubic centimeter is 1 milliliter. You may or may not have needed that, but that's a helpful tool to have in case you do. So because density is mass over volume, you would just do 4 grams divided by 6, and I think you got 0.667. Okay, so that was substance A. Substance B was a little simpler. You just do 10 grams divided by 40 milliliters, and you should have gotten 0.25 gram per milliliter. Substance C was, the volume's already calculated for you, so you just do 30 grams divided by 3.5 cubic centimeters. I think this one was the highest density. 30 divided by 3.5, 8.57 grams per cubic centimeter. And then substance D, you had no work to do, it's just 0.5 gram per cubic centimeter. So here's the numbers we're comparing. Obviously, the most dense is going to be number 1. So you should have said substance C was number 1. That's the most dense. Highest density was C. Okay, the next highest density was substance A. So number 2 would have been A. It had the next highest density. D was the third highest dense, or most dense, and then the least dense was substance B.